Okay, so inscribed angles, by definition, an inscribed angle is an angle whose vertex is now on the circle and whose sides contain chords of the circle, meaning that the sides could extend beyond the circle for that angle. A lot of times we just draw them and stop them at the edge of the circle, but you could extend them. And in one application, here in a little bit, we will need to extend the sides. But an inscribed angle is any angle whose vertex is on the circle. Okay. We've seen this word before, right? We've seen inscribed before. Okay. In the place that we've seen inscribed before may have been when we were looking at whether it be polygons and a triangle. A lot of times we dealt with triangles, but triangles are polygons. But we called that polygon an inscribed polygon, didn't we? Okay. Would you guys agree that if I look at just that angle, is that red angle satisfy the definition that we just created for an inscribed angle? And then does every other angle, maybe if we look at that blue angle, does that blue angle satisfy the definition of an inscribed angle? So then collectively go all the way around. They're all inscribed angles, therefore it's an inscribed polygon. Okay, and we talked about the key to being an inscribed polygon is that the vertices have to be on the circle, right? Okay, because we were trying to meet kind of that unknown definition that we didn't know at the time of what an inscribed angle was. Okay, but we've done a little bit with this type of shape, and specifically what we've dealt with the most is, if you remember, we dealt with, back to chapter 4, we were dealing with a triangle and saying, okay, if I take that triangle, let me hide the circle real quick. If I take that triangle and start manipulating it to where I can find maybe the shape that we, or the point that we refer to as the circumcenter. Okay, you guys remember doing that? Taking the perpendicular bisectors of these three sides, and they go through a point, and when we do that, okay, so maybe that's the triangle I'm looking at. When I then create the circle that is centered at A and goes through B, is that the same as the circle that we started with at the beginning? Does that kind of make sense? Okay. So we've already kind of dealt with a lot of the stuff that we're doing right now. Okay. But we kind of looked at it through the perspective or through the eyes of a triangle and said, okay, if we look at the triangle, can we find the circumscribed circle around it? Okay. Now we're looking at it through the eyes of the circle and say, okay, now let's look at the circle. Can we find the inscribed polygon or the inscribed triangle in this case of that circle? Does that make sense to everybody? So a lot of the facts that we've already learned in chapters 4 and 5 are going to kind of reverberate again through this chapter, but through a different perspective. Okay. And I think that's a very important kind of link to recognize, because if you do get stuck in this chapter and something doesn't make sense to you, hopefully you have built kind of a foundation of facts from chapters 4 and chapters 5 that if you look at it through maybe a different angle or a different perspective, it could help you out and determine what you need to do in this chapter. But those are inscribed angles, and I just want to focus on looking at one of them right now to see a relationship. So I'm going to look at this shape here. Right now, obviously I've got just a central angle here, correct? Okay, and we see that regardless of the size of my circle, okay, we get that relationship that the central angle is always equal to the arc that it intercepts, right? Okay. So we've dealt with that. Those two things equate. Now I'm going to put in a inscribed angle. So that would be an inscribed angle, and I'm going to move it a little bit. Just kind of look at the relationship that we see between this angle here and this angle here. Okay. Let me maybe color this so we can talk about it as the blue angle. So that blue angle is an inscribed angle. Is that all right with everybody? What do you think the relationship between the red angle and that blue angle? Are they going to be the same? Or is one smaller? Is one bigger? What do you think? Maybe if I do this, let's say that, let's take that point D. See if I can, okay, so if D was right there, right, that would be a central angle, correct? But as I pull D away, and even if I go beyond the circle, what is happening to that angle D? Getting smaller, right? If I go closer to the arc, what's happening to it? Getting bigger, right? Okay. So when D is on the circle, okay, when it's an inscribed angle, what I want you to recognize and realize is that that is not the same thing as that angle there. So it cannot be the same as that arc. Does that make sense? But there is a relationship. What do you think the relationship, and maybe I'll move things around here so you can do the math a little bit easier. What's the relationship between that angle, that inscribed angle, and the arc that it intercepts? It's half. Okay? So if I just get rid of that stuff, we see that no matter what that arc is, let's change the arc to 44.33. And let's just go, let's round to one decimal place, makes it, actually, let's do this. Is that easier to see if that is a 1 to 2 relationship? If I change the arc to that, now rounding, so let's, there we go. Is that a 1 to 2 relationship? Okay. And now I'm doing some rounding here, but if I, go out to 5 decimal places, if you took that number there and doubled it, you will get something very close to that number. Okay, out to maybe the 7 might be a little bit different. But no matter what that inscribed angle is, okay, it is always going to be half the intercepted arc. Does that make sense to everybody? Okay. So that's a pretty nice, a pretty useful link that we're going to use. A lot of times you will see this formula here provided, that if I give you, angle B being an inscribed angle, okay, then angle B's measurement is going to be half of AC, arc AC. Okay. And now we're talking about degrees, right? We know we can talk about an arc as a distance or a degree. I haven't done a whole lot with actually using the distance. We'll do that later this week, maybe early next week. But as a degree, the angle and the arc should be in a 1 to 2 relationship. The angle being small. And this is what people struggle with. Is they say, okay, is the arc bigger or is the angle bigger? And my hope to get you to make sure that you understand that is through that exercise of, as I move that from a central angle, as I move that point away from the arc, we saw the angle getting smaller and smaller, right? So then you can make the relationship that the angle is smaller than the arc. Okay. It happens. I mean, we can use in this exercise here, this example here shows us being able to do this with a minor arc. Okay, and you can also do it with a major arc. And if I do it with a major arc, that might also kind of shed light on the fact that angle 2 has to be the smaller thing, the smaller measurement, because would you guys agree that measure of angle 2 is less than 180 degrees? Because it has to be, right? It's an angle that is, 180 degrees would be, a straight angle, right? Okay, this is not that, so that's got to be less than 180 degrees. But if I look at this dotted line right here, is that dotted line to that side of that line there? And if that line's a diameter, right, does that kind of make sense? If that's a diameter, wouldn't this, from that point there to that point there, going in that direction, wouldn't that be 180 degrees? So would you guys agree that that arc right there, that yellow arc, is more than 180 degrees? Okay, so that should hopefully maybe open your eyes to the fact that the angle has to be less than the arc, okay? Because an arc can be greater than 180 degrees, okay? And again, we can see that then here, if I move that to there, okay? The only way that I'm going to get this thing here to be 180 degrees is actually to put those points kind of on top of each other, so that when I zoom in, there is still an angle here. It's just a very, very, very flat angle, right? Okay, kind of like a straight angle there. But if we look at the arc, obviously that red arc is much bigger than 180 degrees. It's almost a full circle. It's 357 degrees. Okay, so that's going to help me maybe remind myself. There we go. Help me remind myself. Now I've got everything backwards. B should be there, and this is just because of the order that I constructed things. So C has to be on the top side of D, and B has to be on the bottom side of D. But the angle should always be smaller than the arc. Okay? It's always a 1-to-2 relationship, though. What happens if I take, let's see if we can do this quickly. So I take that point. What would you call, and now I can't necessarily maybe get this exactly to be a diameter. Oh, I had it. A little overexcited there. Close enough. All right. So would you guys agree that that is pretty close? Let's just do some rounding. That's a diameter, right? Okay. So the arc is 180 degrees, correct? That's a semicircle. Okay. So what then is the blue line? If now take out rounding, okay? But what would that blue angle be? Be a right angle, wouldn't it? Okay. So the way we verbalize that, okay? Because now, as long as I move this point anywhere I want to, is it still intersecting the same arc of 180? Okay. So is it always a right angle? Yeah. Okay. So whenever we have an angle inscribed in a semicircle, that's the way we verbalize it, an angle inscribed in a semicircle, okay, then that angle is a right angle, okay, because the hypotenuse of that right angle is actually the diameter of the circle, right? Or the diameter of the circle is the hypotenuse of the right triangle. Okay? So that's a nice fact that a lot of times we play off of. They ask us about the corollary. It doesn't hold the same kind of clout that a theorem holds because it's not a really hard proof. Because essentially what that stems from is the idea that the inscribed angle is always half the intercepted arc, right? In this case, the intercepted arc is 180 degrees. Half of that's 90. Okay. It just shows up quite a bit that They make it a corollary to say you can just, instead of doing the algebra of 1/2 of 180, you can just say that if it's a semicircle, then make the conclusion right away. That's a 90-degree angle. Okay. So that's a fact that we're going to see kind of play out over and over again. Another fact that we're going to see is, let's say that I look at that there, and we were seeing still the 1 to 2 relationship between these angles. Let's say that I create another angle here. Say I look at that purple angle. What do you think the purple angle's measurement here is going to be? Yeah, because isn't that, if I take out the green angle, or whatever color I had, blue angle maybe, is this now an inscribed angle for this arc here? So isn't this angle here going to be the same as the half of that, which was the same as that angle, right? So these two angles, even if I move E on top of D, you see that they're the same angle, right? Okay. When you have two angles, two inscribed angles that intercept the same arc, then those two angles are congruent. Okay? Because angle D is half of 61.75 by our theorem of inscribed angle measurements. And then angle E is also half of the arc of 61.75. So if you take half of 61.75 2 times and you get different answers, we have issues, right? Okay, so we should recognize that those two angles should always be congruent. And I can put in as many as I want. Okay, so moving around E is kind of showing those infinite other angles that intercept the same arc. So all those angles are going to be the same measurement. Is that doable? Okay. So that I'll put that up so you guys can write that down. If two inscribed angles intercept the same arc, then the angles are congruent. So I'll put in that picture angle 1 and angle 2 would be congruent. So they're both intercepting that green arc. All right, so we've got 2 or 3 theorems here. That's going to allow us to maybe do some problems. So I'll do some examples, and then I'll introduce you to a couple other useful theorems that are very helpful for some of the things that you're going to deal with in your homework tonight. So let's go to slide 6 here. It shows us this picture here. And my background is terrible. All this is asking is, yeah, let's set that to all. Just ask us to find X and Y. Okay. If I go about doing this, in this one, it doesn't really matter which one I try to solve for first, X or Y. So let's just look at X. And what I like to do, it's really nice that it's color-coded here. Take a moment whenever you're doing these problems, because in Math Excel, they're going to be black and white. On worksheets, they're black and white, okay? And, of course, exam, they're probably going to be black and white. My thought is to color over the top of them, okay? Or maybe redraw them, so I'm just focusing on just that information right there. Would you agree that that is the arc that that angle is intercepting? So what does angle X have to be? Yeah, that angle there is 20 degrees. Okay? And if I can use colors like that to draw my attention just to that red stuff, the congestion of the blue angle should not be there. But now if I look at the blue angle, if I look at the blue angle, just focus my attention on that one. Okay, the intercepted arc would be that arc right there, right? How big would that arc right there be? 100. So how big then is this remaining part, y, that we're being asked for? Y would be 60. Okay. So make sure when we're doing those types of things, obviously, the number one wrong answer that I get there for y is 100. Okay. So people just want to double, but make sure that you understand that you've already got part of that 100. Okay. What if I ask you to look at this one? Again, I don't, maybe when I go through this, maybe I focus on B here. Okay, so I'm just going to highlight angle B. And why can I not find angle B?
Which angle is 60? Is that the one with Q or is that the no?
60 is this one here. Okay, so I don't know what A is, so I can't find B right off the bat, right? Okay, but as you're doing these types of things, you might say, well, I know B should be half of whatever A plus 30 is. Would you agree with that? Okay, so maybe you write that formula down, okay, because it is going to be a relationship that you need to know. So if I can't find that, maybe I go to something else and I try to look at A. Maybe I won't find that arc A. So I'm going to highlight the inscribed angle that creates A. Now is there a relationship that I can create or that I can use to find A? What's A going to be? 120. It's got to be double that, right? Okay, so it's double the inscribed angle. Okay, so now if that's 120, we now have B to be half of 120 plus 30. So what's half of 150? 75. Okay. Because then, again, going back and looking at that angle B, it is an inscribed angle for that arc there. And we now know if A is 120 and T to S is 30, that blue arc is 150. F 150, 75. All right? Okay. Got a special corollary here. It's actually a little bit harder to prove than some of the other corollaries that we come through or come in contact with, but we'll go through the proof of this. It's a good algebraic proof to practice. But it simply says if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. Okay? If a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. So angle 1 is opposite to what angle?
3.
Angle 3. And 2 and 4 are then opposite as well, right? Mm-hmm. So we're gonna kind of walk through this proof just with 1 and 3, but you would do a very similar thing with 2 and 4 if you wanted to, if you needed to. All right. So opposite angle. So we are going to look at angle 1, and let's just say angle 1, if I just focus on that there, angle 1 is going to be what in regards to that arc right there? It's going to be half, okay? Do I know what that arc's measurement is right now? No, and it could be anything, right? So let's make it arbitrary. Let's say that is just A degrees. So then measure of angle 1 would equal 1/2 of A degrees, right? Is that okay with everybody? I'm going to then, since I did that with angle 1, and we want to look at its opposite angle, so let's do the same thing with angle 3. So there's angle 3. Would you guys agree that that arc right there is the intercepted arc from that red angle? Okay, do we know that yellow arc's measurement? No. Let's call it, you could call it C. I'm going to use, because we haven't used B yet, so I'm going to use B. But you can call it anything you want to. Okay. My thought though is don't call it A, because you've already used A, right? And then you're saying A and B are the same thing, and the only time that A and B are the same thing is that when we're working with semicircles, right? So we're not proving this for the general case, and we'd be proving it for one specific case. So let's call it B, okay? Where we, and I'll just make the argument here that A is not the same thing as B, okay? So measure of angle 3 would be 1/2 of B degrees. All right. Oh, let's look at this picture. Maybe all right, but we know that A plus B should equal what? If I look at this picture, should be 360 degrees, right? Gives me the entire circle. Okay, so measure of angle 1 equals 1/2. Measure of angle 3, or 1/2 A. Measure of angle 3 equals 1/2 B. But we know that measure of angle, or arc A plus arc B is 360 degrees. If I say measure of angle 1 plus measure of angle 3, what could you rewrite that as algebraically? What is 1 equal to? 1/2 A, right? What is 3 equal to? 1/2 B. Does that make sense to everybody? Just using substitution. I define that because I know, because they're saying that 1 plus 3 has to equal 180, right? So I'm trying to see if we can show 1 plus 3 somewhere algebraically, and then hopefully maybe through a little bit of work, we can turn that 1/2 A plus 1/2 B into 180 somehow. Okay? What do you recognize occurring over here? What do those two terms have in common? Yeah, they got that 1/2 in common. So can I factor that 1/2 out? Does that make sense? Then through substitution, doesn't measure of angle 1 plus measure of angle 3 equal 1/2? What did we say A plus B was? 360. What's half of 360? And then we would say, by definition then, angle 1 and angle 3 are supplementary angles, correct? Okay. And that's an algebraic proof of our geometry concept here. Okay. And now because we chose A and B to be arbitrary, and ultimately angle 1 and angle 3 are arbitrary because they come in 2 and 4, we have proven now that opposite angles of an inscribed polygon are always supplementary. So what do all 4 angles add up to? 360. And that's a fact that we already knew because it's quadrilateral anyways, but is that okay? There's a question in your homework that it's specific. It's a they'll put like B as some degree, okay, and then we'll use some other arcs throughout here, but they won't give you all of this purple arc maybe, and maybe they give you angle 2, and it's usually a question that you have to fight through. People struggle with it. We'll talk about it tomorrow, but I just kind of want to warn you that in your homework. This corollary gets addressed a couple times in that homework assignment. Let's move on to this thing here. Now, I don't like this picture. I created this PowerPoint before I ever used GeoGebra. So let's see. Let's go to this, and I will give you what that slide is talking about in a better picture. All right, so if I look at this inscribed angle, and right now that's an inscribed angle, and we obviously know the relationship between that angle and that arc to be a 1 to 2 relationship. As I start moving this point B, is it still a 1 to 2 relationship? Yep, still a 1 to 2 relationship, right? Okay. And if you don't, believe me, that's a 1 to 2 relationship, even with the rounding, because of the rounding. Maybe I come over here and I say, if I take beta, which beta is the red or the green angle, and divide that by then alpha, which is this one here, we see that it gives that 0.5, right? So it is a 1 to 2 relationship, and it's a 1 to 2 relationship wherever I put B. Now, what's happening at B is getting closer and closer to what point here? Getting closer and closer to D, isn't it? Okay. Now, if I zoom in, we start to see that this is still an inscribed angle, because an inscribed angle is an angle that's created by the vertexes on the circle, and the sides of the angle are chords of the circle, right? So is that still, the black line is the black segment that you're seeing here, or curve still, is the circle. Does that make sense? Okay. But because I'm zooming in, it's starting to look more linear, isn't it? And that's kind of a calculus idea. But as I move B and D closer to one another, okay, they're really close right now, but I should still be able to zoom in far enough to see, because B and D are not the same point. As I zoom in, eventually, you're starting to see it right now, there's still a gap between the circle and that line, right? So it's still a chord, therefore it's still an inscribed angle, right? Okay, so I should theoretically be able to get B and D to a point that we say is infinitely close to one another, right? So like the distance between B and D is like 0.0, as many zeros you can put in a 1, so that I still have that blue chord. And if I have that blue chord, what's the relationship between the red arc and the angle created? It's still a 1 to 2 relationship, right? Okay. What happens then? The question is, what happens when does this angle here of 119.81, as I move B and D infinitely close to one another, and eventually B stops right on top of D. Even if I come over here, is that 119.81 changing very much? It's not changing all the way we see it, right? Now, if I put more decimals on there, it's changing quite a bit there, but the closer and closer, that 812 of that decimal is constant, right? That doesn't change, okay? So as I get closer and closer, that amount is not changing very much, okay? So can the arc change very much? No, okay? So when I divide them, does that thing there change very much? No. And when I make that distance infinitely small, or maybe I even make it disappear, I now put B on top of D. Do I still have a 1 to 2 relationship between the arc and the angle? But now the angle is not, that angle is not an inscribed angle anymore, because this chord, because that was the chord on the inside, right? When it was on the inside of the circle, when B and D were different points, that chord has now turned into a, what kind of line? Or what kind of red if it touches my circle one time? That's with a T tangent, okay? So that blue ray on the outside of the circle is a tangent. The blue one on the inside is still a chord, right? So we call this blue angle, okay? And when I talk about this blue angle, I'm talking, let me put a point right here and go from C to D to E. Oh, guess we got to go the other direction. E to D to C. And let me just look at the properties of this and change it to maybe that color. Make it that big. Let's do cross hatching. Now we're talking about that angle right there. Does that make sense to everybody? Okay. That's no longer an inscribed angle because it's not created by two chords. Okay. We call that an angle that's created by a chord and a tangent. Okay. Not a really fancy name, right? The angle created by a chord and a tangent. But what's the relationship? That angle you're seeing is 119.81299. It is still half of the red arc. Does that make sense? So that red arc is still created by that angle, and we still get that 1 to 2 relationship. And the proof of that, kind of using maybe a calculus approach here, is showing that as I move, that right now it's an inscribed angle, right? As I move B closer and closer to D, that inscribed angle turns into an angle created by a chord and a tangent, but the variance in the degrees is not changing very much, so this relationship is still 1 to 2. Okay, that's a theorem that a lot of people, it's a relationship that a lot of people mess up. One of the things that people like to mess up with on that is this idea here. If I look at this picture, this example, what's the red arc there going to be? 130 degrees, because the blue one and the red one have to equal a whole circle, right? So now using the relationship that we just talked about, this red arc is created by that tangent and that chord, right? Would you agree that red arc is on the inside of that angle? Okay, so that arc then is 130, so this angle here is going to be, again, half that. Does that make sense, everybody? What people struggle with, and they're never going to ask this, but for some reason people want to try to figure this out, which you can't, is that they want to say that this here is an angle. And my question to you, is that an angle? Why is that not an angle? What is the definition of an angle? Okay, it's two rays that share a common vertex, right? Is that blue thing a ray? Well, what's a ray? Just a portion of a line, right? So that's a ray. Is that a ray? No, because a ray is a portion of a line, right? Lines can't be curved. Okay? And then for the same reason, some people want to think about that as being the angle that we're trying to find when we do this. That is not the angle. It's not an angle, right? Okay? It's the sum of this red stuff and green stuff that theorem is getting at. That sum is the angle created by a chord and a tangent. Okay? Yes.
So if there was like a line going all the way around the world, it would be a line.
Correct. It would be if you took a line right now and drew it all the way around the world, it came back to where you are right now. What do you trace out? You trace out a circle. Okay. So there is an assignment 12.3. It's going to address these